Last time we were talking about vectors, and a couple weeks ago we talked about vectors and scalars and the difference. And so a vector is a quantity that can be represented by an arrow. It has both magnitude, which is represented by the length, and direction, which is the tilde angle. A scalar is just a number. It doesn't have any direction. So what happens if you take your vector quantity, your A vector, and you multiply it by a scalar like 2? Well, what's nice is the scalar just adjusts the length. That's all it does. It just adjusts the length. And so if we wanted, for example, then, a new vector, 2a, well, it says take your A vector, which we know how long it is and what angle it points, and what you're going to do is you're going to multiply it by 2, which just means, as you might have guessed, make it twice as long. So there's your 2a vector. Anytime you want to multiply a vector by a scalar, it just adjusts the length. Multiply it by 3, makes it 3 times bigger. Multiply it by half, it shortens it by a factor of 2. That's the whole vector-scalar relationship, and it's going to be very important coming up. All right. Now for something kind of complicated. We have ways to represent vectors that exist outside of just the geometric way. So in the last lesson, I was talking about how you could have an R vector that determines the position of an object. And in the last one we said, oh, well, let's take we know that it's 3 to the right and it's 4 up. So that's the actual object right there. But we can represent its position with a vector that's drawn from the 0, from the origin, out to the position. So this is our R vector. And we said that the R in the x direction is equal to 3, the R in the y direction is equal to 4. And we could use the Pythagorean theorem to get the actual length of this, and then we could use trigonometry to get the angle. It's very much like polar coordinates. It works the same way, but we're not going to do that specifically. We know from our just general understanding of the world here that this is the x direction and this is the y direction. So how do we write our vector? There's a couple ways. I could say that the R vector itself is equal to the Rx vector plus the Ry vector. This means not just add them together, because that wouldn't make any sense, because 3 plus 4 doesn't equal 5, but because we have the vector notation on top, it's telling us that we have to add them like vectors, which means you take your Rx vector. Here's my Rx vector. I'm going to add it tip to tail to the Ry vector. To get the actual R vector, which is here. So that's our understanding of this. That's how we get this. So the magnitude of this vector is 3, the magnitude of this vector is 4, but when we make them vectors, we have to include the directions that they point. That's fine. But here's what they do to make things complicated. Is they don't say, I'm going to call this the x direction, and I'm going to call this the y direction. They give them new titles just to confuse you. Okay? And so what they say is that this Rx vector has length 3, and it points in the positive x direction. So here's how they do it. They designate 3 new vectors that they call the unit vectors. Unit vectors are interesting because if you notice this word right here, unit, you've seen it in a different context, right? What's everybody's favorite circle? That's right, it's the unit circle. And what's special about the unit circle? The unit circle is special because it has a radius of 1. That's why we call it the unit circle. So what we're saying is that this word unit here is a secret physics and math code word for 1. So a unit vector it has length 1 and it points in either the x, the y, or the z direction. And yes, we are adding the z direction here. We'll see how that manifests in a couple of minutes. But it has length 1 and it points in either the x, y, or z direction. So here's how we're going to name this now. Watch this. This is cool. Instead of writing it rx and ry, we're actually going to tell it exactly what's going on here. So if I want to write my position vector for this guy right here, I'm going to say that my r vector, oh, sorry, I forgot to tell you what the names were. The one that points in the x direction is called I. The one that points in the y direction is called j. And the one that points in the z direction is called, you guessed it, k. But then they do a funny thing to indicate that these are the unit vectors, is they give them a special symbol. We call it the hat. So I hat, j hat, and k hat are our 3 unit vectors. So how do I express this r? Well, I know that it's 3 in the x direction and 4 in the y direction and no 0 direction. So my r vector is going to be equal to 3 I hat, which means it's 3 in the positive x direction, plus 4 j hat, which means it's 4 in the up direction. And this is called unit vector notation, and it's not challenging. It just means like, oh, I know it's 3 in the x direction plus 4 in the y direction, which is going to give me 5 in the xy direction. Not that hard. So how do we use this? Okay, how do we use this to manifest some more complicated problems? Well, let's say I have 2 vectors that I want to add. Let's say I have 2 vectors that I want to add together. Okay, I have 2 vectors that I want to add together. So I have 2 vectors. One is so we'll call this vector A, and vector B is here. Now, I could add those tip to tail and do it graphically, I could do it geometrically, but what if I had their equations in unit vector notation? That would be really cool. So the A vector, okay, the A vector is equal to, I'm checking my notes, hold on. Is 8i plus 15j. And the B vector is equal to 12i plus 5j. Now, if you're playing along, you may have noticed right away that these I and j, those are the actual components. So for example, this one right here, this is $15 up and 8 over, and this one here is 12 over and 5 up. So given these criteria here, I can just add them together. So if I want to get a plus b as a new vector, well, I'm just going to add. What's a plus 12? So I have 20 in the I direction plus 20 in the j direction. So I have 15 up and 5 up plus 8 to the right and 12 to the right. So here's my new vector. And then now, given this, we could draw it on a coordinate plane. And we can see that our new vector is 20 to the right and 20 up. And then using a little trigonometry, we can realize this is obviously a 45-degree angle, and this is about 28 long, about 28, maybe a little more than 28, maybe 28, 29. So we're going to be using the unit vector notation, and if I just want a unit vector by itself, a unit vector has length 1, and it points in either the x, y, or z direction. So I hat has length 1 and points to the right or left if it's negative. J up or down, and k left or it's the z direction. It's either in or out. It's in or out. All right. Since we mentioned the z direction, let's go a little bit farther here and let's see how does the z direction actually manifest. It's cool because we're really familiar with the xy direction. And we talk about it all the time and we have no problem pointing it, but what about the z direction? What about the z direction? What if I told you that I'm looking for a point, okay? I'm looking for a point that's 6 to the right, 3 up, and 2 back into the board. So it's 6 to the right, 3 up, and 2 back into the board. Well, that would be an R vector for this point. That would be 6 in the I direction plus 3 in the j direction minus 2 in the k direction. So where is that? Like if this is x and this is y, where's the z? Well, the way that we draw it kind of looks like this. So the z is pointing out at us, and then this z is going back. This is the positive z here. This is the negative z in that direction. This is the positive x. This is the positive y. So how are we even going to plot that, right? How are we even going to plot that? Well, we got to go 6 to the right. So 1, 2, 3, 4, 5, 6. I go 3 up, 1, 2, 3, and then 2 back. 2 back. Well, that would be back along this axis here. So let's see if we can do it in green. Okay. So I'm going to go 6 to the right. 6 to the right, 3 up. Okay. So just to get to that point, it'd be 6 to the right and 3 up. If I were to make a little rectangle here, okay, but I still have to go back into the board, 2. So back into the board would be along this axis here. We're going to make it into 3 dimensions now. So I went backward along that z-axis, to get to this point right here. That on this coordinate plane is 6, 3, -2. It's back there. But here's the real question. Now that we've drawn it, I want to know how far away from the 0 is it? If you had to go get there, I mean, you could walk 6, 3, and 2, right? If you walk linearly on all 3 of those, right? 6 plus 3 plus 2, that would give you 11, but I want to know how far back it is if I were to go straight through this rectangle. How am I ever going to find that distance through that rectangle? Well, it turns out that Pythagoras, not only did he have a construct for 2-dimensional triangles, but the Pythagorean theorem actually works for 3-dimensional straight lines also. So we rewrite the Pythagorean theorem to be in 3 dimensions instead of 2. So we say that a squared plus b squared plus